Nothing. Okay, this is one experiment that you see here. And then there was other philosophical question here. How much you can rely on experiment? Because the source of knowledge was uh, random stuff. The source of knowledge was facts coming from the past, from ancient philosophers, from discussions and reasoning. Now you are using what? Mixing two things or observing something. It happens in a very short time, and it's going to happen the same way all the time. Is it original? Is it a proved way, verified way to discover facts? Okay, you drop something, I don't know, from a distance and measure its acceleration, its velocity. It's going to happen the same way all the way. You go to top of a mountain, you go to the, I don't know, sea level. So there were some doubts about uh, the originality or the reliability of experiments. But what was so important here that by the publications happened in these society, in these learned societies, and in the form of books and journals, and then they performed these experiments in public sphere, in the libraries, I don't know, in city halls, in pubs and gathering places, then everybody could practice that. It was not a one-man show story. So uh, as you see here, Alfonso, the king of Spain, says that old wood, old wine, old friends, and old books are reliable. It means that in the all the stuff you can find originality and truth. Now we are doing some experiment which is a temporal and a short time verification of something, and can be used as the source of truth. Experiment was so important that people like Robert Hooke wanted to experience and write the first-hand report of experiencing what a vacuum chamber. He ordered a big vacuum chamber in a size that he was able to enter in it, and then they sealed that, and they started to vacuumize the air. Fortunately, the pump didn't work to stop working, otherwise they would kill the guy, the scientist. He wanted to see what happens in suffocation, and but he suffered from ear pain because the eardrums pop out when you are in a vacuum chamber, and that was the what first it shows how eager these people were in scientific investigation to discover unknown stuff, and at the same time they dare to perform experiments even on their own body, and they just accepted to be a part of the experiment. So I talked about this slide that this Royal Society, they created a kind of open science. They didn't have hidden science uh, to hide all the I don't know, calculations that they had, approach that they had. Now they provided the details of their experiments, their calculations, their observations to everybody, and discuss them openly, as we see, for example, at the same time, Thomas Hobbes, one of the philosophers that one of the thinkers of this period. So he talks about that if you would like to do it, to do the same scientific experiment or uh, the same experience, you are very welcome. Everything is outside. It is in the what's called access of everybody who's interested, and you can do it wherever you want. And uh, it is again is not a part of this book, but he doesn't talk about this. But in mid 18th century, uh, we had many peoples traveling all around Europe in big cities. They carried all experimental instruments and devices that they had to perform experiments for public in public places. And that was also the time for the first time women were able to encounter with this modern science, because they were not allowed to go to universities that time. If they were um, very wealthy, they would hire a tutor to teach them about science, specifically modern science. But uh, during this presentation of science to public, many people learned about new discoveries. Uh, One very specific field related to electricity, static electricity, had a lot of innovations and inventions and discoveries there, because some of these presenters of um, electric phenomena, they had just shows to entertain people. They uh, what made business based on that, because they collect money. So they had advertisement that on such and such day we're going to show um, electric experiments, and people had to pay something to see. And to make the experiment very exciting, they came up with some innovations, some new ideas, which the originators of those experiments never thought about them. And we see that some of these presenters also later became scientists and some inventors in electricity. So this was again one of the characteristic features of this this period. So they did experiment and they published about this because it uh, made them uh, famous. We see a good number of people who were amateur scientists. They were not professionals coming from universities. They learned little by little uh, through this public sphere or by reading the available books. And then later they became scientists, very well known uh, people. And by the end of 18th century, we see that mathematics and physics, they merge, and mathematics becomes an inseparable part of physics. Physics in the classical era, in Greek tradition, in medieval tradition, was a part of philosophy. It was called natural philosophy. There was no mathematics in it. There was no experiment. There was no concept of universal law in physics. But after, uh, specifically after Newton, before Newton, we have some other scientists like Kepler or Galileo. They expressed their discoveries in mathematics, but it was Newton who introduced these universal laws, mathematized physics, and then we entered into a new era talking about new physics, which came out of philosophical thoughts, out of philosophy chamber into a real physical world, and our questions were changed from why question to how question. I believe the first day of this lecture, this course, I talked about this, but I'm repeating it. Why question is the approach that to answer the why question was the approach that we had in Aristotelian physics. So why this paperclip falls? Because it is heavy and its natural place is on uh, the ground, in the heavy part of the universe, which is the Earth, and you explain it. Okay, you could add uh, Aristotle's four causes to explain other things. Again, the same thing. Why I teach here, okay, because I want to educate you. You learn about history of science, and that's it. Okay, I explained it. Uh, why the moon is round? Because it belongs to celestial sphere, and celestial region is the region of the most perfect objects, and the most perfect geometrical shape that we have is a sphere. Then that's you explain it. But how question is a different type of question. You, in answering how question, you may not care at all about why question. Okay, why does it fall? Okay, why you can say it falls because of curvature of space and time. You can say that it falls because of the impact of very small particles called gravitons, or you make the different stories. But when you answer how question, it means that you have to observe the process of a free fall. You have to observe that this object is falling from point A to point B. It is such and such distance. It falls in such and such time. And you again observe it carefully to see if it falls smoothly with the same speed or its speed changes. Then you discover another thing named acceleration, and so on and so forth. The same thing, for example, we have why cancer happens in, I don't know, in some of our cells. We don't know. People are working on it, but we can describe how it happens. And then we try to describe it and find a solution uh, for that. So Aristotle's approach was to explain things as they are in this universe, as they exist, as they are there. But uh, Galileo's approach and later Newton's approach was what? How to describe it. And when you describe it, you enter in the process of measurements, in producing data, in analyzing data, and then find out about the mathematics behind natural phenomena. Another aspect of this period also is how to get rid of the concept, we call it common sense. So everybody uh, sees that the sun is rising and setting. It is a common sense. It's common sense that you have a lot of other ideas that everybody agrees that's correct, but uh, we see only the appearance of things like the motion of moon around the earth, motion of the sun around. How can we verify what we call it common sense? How can we verify that really the sun is moving around us, or there is another phenomenon? So this moving from common sense to verified facts again needed very accurate observations, measurements, and finding out the mathematical principles, the real physics of everything. And again, it is uh, described by how to answer how question. rather than why question. So Descartes, for example, argues about this common sense, what says that you have to verify. Uh, don't just accept uh, statements from authorities, either religious authorities or philosophical authorities. You have to verify everything yourself if it's possible, and then accept it after detailed study of the phenomena that you are studying. In modern science, we see that a lot of new instruments, scientific instruments, appear and they became a part of the practice of science. So telescope, we already talked about telescope, but microscope was uh, another invention this time, which opened window to see very small and invisible stuff. For centuries, people at least knew about stars, planets, they observed them, but we didn't know anything about small stuff. We didn't know about the structure of the, I don't know, compound eye of an insect. So when again in this culture, in this very religious culture, they started to see both macrocosm and microcosm. They found that in macrocosm, they already discovered rules, the laws of gravity, laws of planetary motions. Everything was based on order. And when they dive into very small structures, from the snowflakes to the, I don't know, body of insects, they found also there are perfect designs, geometrical designs. And it is very interesting that after the invention of microscope and making of better and better microscopes, this natural theology actually developed a lot. You remember natural theology was a theology how to use natural discovery or discoveries that we had in the natural world and apply it in theology. And by invention of microscope, we see that a lot of new studies started to find order and laws in the micro world. So they had this drawings of the flies of eyes of fly, and then they were thinking about a designer who put all these single eyes in a mathematical order there. Let's watch this short video about Le Perchet and invention of microscope.
Thanks to CuriosityStream for supporting this episode. Go to curiositystream.com/microcosmos to start streaming thousands of documentaries and nonfiction shows.
Let's pass this advertisement.
In the year 1675, I discovered very small living creatures in rainwater, which had stood but few days in a new earthen pot, glazed blue within. Those are the famous words that Antony van Leeuwenhoek used to describe microbes. Though he didn't use the word microbe, he called them animalcules, and the letter itself is not exactly the one he wrote. Leeuwenhoek's version was written, of course, in Dutch, and then sent off to Henry Oldenburg, the secretary of the Royal Society in London, who founded the publication Philosophical Transactions. Oldenburg translated Leeuwenhoek's work into English and published it in 1677. The rest, as they say, is microbiology. In 1932, the scientist Clifford Dobell published a biography of Leeuwenhoek called Antony van Leeuwenhoek and His Little Animals. Dobell introduced his subject with some self-consciousness for taking on the story of someone who, if you've been interested in microscopy, you have almost certainly heard of. And he wrote, "Dear reader, I know full well that you and everyone else must have met Mr. van Leeuwenhoek many a time before, but please let me reintroduce him to you, for he is a man worth knowing more intimately. Though he was born exactly 300 years ago, he is still very much alive and would be glad to make your better acquaintance, provided only that you are, quote, a true lover of learning, as of course you are." The fascination with Leeuwenhoek's work for Dobell and so many of us lies in the scope of Leeuwenhoek's curiosity and the writing that documented many of his journeys into the microcosmos. Born in the Netherlands in 1632, Leeuwenhoek was a draper by trade, meaning that he sold cloth. He took up microscopy as a hobby, learning to grind lenses and turn them into a tool to see into tiny worlds. The simple microscopes he built were better than many of those of his contemporaries, producing images that were both more magnified and more clear, though of course compared with what the average high school biology class has today, they were very bad at both of those things. The creatures Leeuwenhoek described in his 1677 publication were not his first description of tiny animals in water, though. In 1674, he wrote of green streaks spirally wound, a description that later observers have taken to refer to the filamentous green algae Spirogyra. He also wrote of little creatures he'd found that were, as he described them, 1,000 times smaller than the smallest ones I have ever yet seen upon the rind of cheese. Those little cheese rind creatures he was describing were likely mites. Reading Leeuwenhoek's work, it's kind of like following an old treasure map. His words lay out pathways and clues that help us navigate through a drop of 17th century water. And if you follow that map, at the end you find a wealth of information, the knowledge of microbes and their identities that was still unknown in his time, but that in the centuries since has been accumulated. For Dobell, Leeuwenhoek's 20th century scientist biographer, this treasure hunt was a long one, born out of his own enchantment with these original discoveries and a desire to better understand them. He learned Dutch only to find that the 17th century Dutch of Leeuwenhoek's letters was impenetrable to him, and with World War I raging around him, he had to set aside his attempts to translate Leeuwenhoek's work for some time. But eventually, through what seems to be largely a lot of determination, Dobell was able to work his way through Leeuwenhoek's letters, and that labor of love led naturally to translating things like Leeuwenhoek's descriptions of his own poop. Per Dobell, Leeuwenhoek wrote the following: I have usually, of a morning, a well-formed stool, but hitherto I have had sometimes a looseness of the bowels, my excrement being so thin, I was at diverse times constrained to examine it. But Leeuwenhoek wasn't documenting his stool just for the sake of it. In that sample, he saw an opportunity to observe the animals within. I have at times seen very prettily moving animalcules. Their bodies were somewhat longer than broad, and their belly, which was flattened, provided with several feet, with which they made such a movement through the clear medium and the globules that we might fancy we saw a pissabed running up against a wall. That description sounds promising, but Dobell had a problem. Leeuwenhoek had compared his microbes to a pissabed, and like you and I, Dobell had no idea what a pissabed was. Even the original English translation he'd read shrugged it off as a Dutch term with no obvious English equivalent. Dobell had to find a 17th century Dutch English dictionary to figure out that a pissabed is a woodlouse. And with that reference point, Dobell had enough to diagnose Leeuwenhoek. Very belatedly, of course, with Giardia, the product of a flagellate known as Giardia intestinalis. At the time Leeuwenhoek was identifying the microbial residence of his stool, he almost certainly didn't know their role in his poor digestion, nor did he, of course, have any name for them or any of the other microbes that we now know he saw. And yet we can identify rotifers from his characterization of their wheeled heads, and Vorticella from his description of their belled bodies. The irony of our centuries later fascination with reconstructing and replicating Leeuwenhoek's work is that his contemporaries had a much harder time of it. Leeuwenhoek didn't help his cause much, refusing to provide extensive details of his methods, and even keeping his microscope building techniques to himself.
Okay, let's stop here. It disconnects back to back. But yeah, that was the discovery that the invention that opened windows to many, many discoveries and had impact not only on science, but also on theology and natural theology and discussion about argument from design. We already talked about argument from design, that how to find this complex uh, mechanisms in nature and then attribute it to a designer. So you find in microbes, in very small creatures in the universe, in our eyes, and everything that you um, uh, investigate and find a complicated mechanism there, then that complicated mechanism definitely needs a designer. And up to uh, the end of 19th century and the first half of beginning of 20th century also, we see that how this approach was part of all intellectual activities, all philosophical activities to discover in science, and at the same time use it in theology to prove that there's a designer. So using microscope, we see that people like Henry Baker, he started to look at sands. Okay, now you look at microorganisms, and obviously they are very fascinating. They are moving, they are interacting with each other. But how about dead stuff like um, sand? And he discovered a lot of beautiful shapes there in the shape of cubes, I don't know, pyramids, hexagons, and so on and so forth. And he started to categorized them, studied them, and the uh, uh, conclusion was that with great mechanical exactness, then the most skillful hand could draw them. So all these sands were made by a creator who knows mathematics better than everyone. Okay, we already talked about Newton's cosmology, uh, which was different than Descartes' cosmology. In Descartes' cosmology, uh, universe was like a clockwork, and after creation, God just give him an energy, or by winding them, put some energy inside that, or motion inside that, and it works forever. But in Newton's universe, after discovery of gravity and motion of the planets, for gravity, he needed an ether to communicate gravitational forces. After discovery of comets, that they were celestial and they spread uh, their tails, materials, particles in the solar system, they create friction between planets and um, the medium around them in ether. Also, they developed the theory of stars. They were thinking that the sun in our solar system, it burns and it leaves, it lose some of its mass in the form of vapor, and that vapor also fills the solar system. Then this solar system cannot be eternal. It cannot be in order because the friction between planets and the ether can end up the motion, planetary motion. Then they needed a natural agent, but designed by God to regulate the motion of the solar system. And in Newton's cosmology, uh, it was the comet doing that, and comets were messengers of God to come and regulate the motion of the solar system. Uh, but this idea, which was very attractive that time, and again, it added to Newton's fame, which he discovered about the nature of comets as members of solar system and connected it to theology. But little by little, by more discoveries about comets, many questions appeared like this. Okay, why uh, comets are random? If this exhalations, if this evaporation of the sun happens in a regular way with the same rate, uh, why comets come random? They should appear in a very orderly way, because you know how much friction that you have, how much evaporation that you have. Then probably every 50 years you want to. Then another question was about the number of comets. By that time, hundreds of comets were listed. And then this bigger question appeared, that is really the solar system, is that vulnerable and in chaos that you need hundreds of comets to come and regulate its motion. Then we see that by the end of 18th century and beginning of 19th century, by having better and better telescopes and measurement tools, and also using the science coming from Newton, which was refined and got better by Simon Laplace, Pierre Simon Laplace, they discovered that comets were not that big. They cannot have that influence on the, I don't know, dynamics of the solar system. They are really small. Laplace calculated the mass of a comet should be less than 1/5,000th of mass of this Earth. So they discovered comets were very small. Then later they discovered about their density, which was very low. Then Newton's cometary theory connected to cosmology actually vanished. So what do we see here? We see a gradual shift in Newtonian physics and cosmology connected to theology shifts towards a kind of deterministic cosmology in which you don't need the interference of God that many times to regulate the motions in the solar system. So though Newtonian physics, Newtonian celestial mechanics had a direct connection to theology. Later, we see that by um, uh, finding more about motion of comets, by finding about perturbation in the solar system, which developed by Laplace. He solved n-body problem. Uh, Actually, he had a better understanding of n-body problem, and by application of Newtonian physics and observation of many other objects in the sky, uh, we see that a modern cosmology appears, which is totally deterministic. For example, by the time of Laplace, telescopes were big enough to resolve some of the nebula in their details. So we have stars on the sky, and then which they twinkle. We have planets, which with big telescopes you can see them as dots, as coins, as circles. But we see some uh, what pieces like a piece of cotton, which they don't have very round or well-defined edges. They are like a bunch of cotton in a spiral form. They call them nebula. Nebula means cloud. Actually, they saw these small clouds, and by improvement in or telescopic observations, we found that some of them are really spiral. Okay, so now you can imagine that these objects are very, very big clouds. Then, little by little, apply Newtonian gravity and Newtonian rules, Newtonian laws to this uh, spiraling cloud. Then what happens? According to Newton, the law of gravity, this cloud start to shrink because of gravitational attraction. And then when it shrinks, based on another concept that Newton developed, conservation of angular momentum, it starts to rotate faster and faster. When it rotates faster and faster, again, based on another rule of Mr. Newton, it flattens the same way that you flatten pizza dough by spinning it faster and faster. And then you end up to what? This gas cloud flattens and comes to one plane, and then at the center you have too much mass because of gravity, so you have a central bulge or central star, later you can call it, and then around them you have a lot of these particles are moving, and they can also condense and make what little objects moving around this big object, and in this way you can talk about formation of solar system. just based on laws of nature. This is actually the culmination of this uh, cosmological ideas, which by applying discovered natural laws, by applying mathematics, you could talk about formation of solar system without involving a creator, avoiding argument from design. And it happened by Laplace, who used ideas from Immanuel Kant, which was a great German physicist, philosopher, and he used Newtonian mechanics and celestial mechanics, and he developed a theory which is called the nebular theory of the solar system. And it is very interesting. Napoleon visited uh, Laplace, and he explained his idea about formation of solar system. And Napoleon asked, okay, where is, you didn't talk about God in this theory. And he said that, Your Honor, I had no need of that hypothesis. It means that everything can happen by itself based on the laws that we have in nature. So this is the outcome of all discoveries that we had in uh, mathematical astronomy, in mathematical physics, in describing universal laws and combining them and uh, making science so powerful to explain everything in this universe by just scientific rules. Okay, so we see that science also takes distance from theology. Okay, you are very welcome. You are a believer. You can have your beliefs and just continue as a private practice. But when you are doing your science, when you are talking about the structure of the universe or observations that we have, the natural phenomena, then there you have to just to do your scientific job. Okay, uh, religion or your theology or your philosophy can provide ambition for you, or they can act like a driving engine. But when you are solving a differential equation, you are just scientists, you are involved in that project. When you are uh, trying to think about, I don't know, dark matter or dark energy, then you have to just use facts and apply whatever you know about this universe and theorize about that. When you involve another uh, idea coming from unverified sources, coming from your philosophy, coming from your theology, then it is not a true practice of uh, science. Okay. Okay, this is the bottom line of the third book that we studied. I don't have more slides to show. Actually, it is the last concept that is discussed in this book. Then I end today's lecture earlier. It is the last class that we have. I posted the uh, assignment page to drop IEval participation screenshot. And then we're going to have our final exam on Friday, which is from 1 to 3. I don't remember exactly, but once I talked, I don't know, this class or my next class, I can extend it to 2 hours, 3 minutes. But I modify it and you will have 2 hours, 3 minutes to take the exam. It will be online. Again, your videos should be open, and exactly at the exam time, you will see questions on Canvas. and do the same thing that you did in previous writing assignments. Okay, before I end this lecture, any questions, any comments, any ideas? I hope you liked this class. Uh, sessions were long, very tiring, but you'll gain something, you lose something. We did this in 5 weeks instead of 10 weeks. Okay, folks, no questions. I end today's lecture. Perfect. We have a great time and hope to see some of you guys during fall, which we have in-person classes. Bye, everybody.